Okay, and for our last talk today, we have a pleasure to welcome our neighbor from Université Paris-Saclay, but as you all know, Université Paris-Saclay is Orsay. Here we are in CEA Paris-Saclay, which we are currently standing in Gif-sur-Yvette, so, but Paris-Saclay does not really exist, but that's my... so, yeah, virtually, yes, okay. But okay, joke aside, it's a pleasure to welcome Jean-François, and he will talk about local times of Brownian motion indexed by the Brownian tree and the volume of spheres in the Brownian plane.
Thank you, Jeremy. So it's a great pleasure for me to be speaking here in this conference in honor of Emmanuel. So I think we have interacted a lot in the last 20 years, and in particular in this working seminar we had at Orsay at the end of the year 2000, and also, of course, in the Journée Carte since many times. Okay. And I think the work of Emmanuel has influenced a lot my own work, and certainly I was happy to interact with him. So today I want to speak about local times of Brownian motion indexed by the Brownian tree, and so here is an outline of the lecture. So my interest is in these models of random geometry known as the Brownian sphere or the Brownian plane, which arise as scaling limits, continuous limits of large random planar maps. And one construction, the original construction at least of these models, was based on the building block, which is this Brownian motion indexed by the Brownian tree, which I will define later in the lecture. And you should view this construction as just a continuous version of the bijections between planar maps and labeled trees, and I refer, of course, here again to the papers by Cory Vauquelin, by Gilles Schoffer, and by Jérémy, Philippe, and Emmanuel. And this last paper in particular was important for me in several papers I wrote. Okay. Let me also say that there is an alternative construction of the Brownian sphere, which is due to Jason and Scott Sheffield, which is based on completely different ingredients, but I will not talk about that today. Okay. And so my goal in this lecture, in fact, is to understand the local times of this object, the Brownian motion indexed by the Brownian tree, and in the setting of random geometries, it means looking at the volumes of spheres in the Brownian sphere or in the Brownian plane. Okay. And it turns out, as we will see, that these local times can be described by a stochastic differential equation, which is with explicit coefficient. Okay? And the results are, in my opinion, particularly nice than when you look at the setting of the Brownian plane, where you really have the distribution of the process of volumes of spheres. Okay, so I will explain that later in greater detail. So in the first part of the lecture, I will give a kind of reminder about what we know about well, at least about the construction of the Brownian sphere and some properties. And the first key ingredient, so there will be some overlap with the lecture by Gregory yesterday, but my approach is slightly different. Okay. So key ingredient is the Brownian CRT, which was introduced by David Aldous, which is a kind of continuous limit for many models of discrete trees, in fact. Okay. And the way I like to see the Brownian CRT is as a tree coded by a normalized Brownian excursion. So normalized means that the duration of the excursion is equal to 1. So later it will be different, in fact. And so you should think of a piece of Brownian motion, you see indexed, so it's indexed by the interval 0, 1, and you look at the Brownian motion started from 0 at time 0, conditioned to be back at 0 at time 1, and to stay positive on the interval 0, 1. So this is a normalized excursion. And we can associate with such an excursion a tree, which I call the tree coded by the excursion, denoted here by TE. And how do we get this tree? Informally, what we're going to do, we're going to consider all horizontal chords drawn below the graph of the excursion. So of course in this picture I have drawn only a few of them, but there are infinitely many, of course. And each time we have such a chord, we are going to identify the endpoints of the chord. Okay? So you should think of the graph as if you want a strip of paper, and what you do, you glue together 2 points which correspond to the extremity of a chord. Okay? And if you do this gluing procedure, what you get, in fact, is a tree, which I call the tree coded by the excursion. It's not a discrete tree, of course, it's a continuous tree. It's a continuous random tree because the excursion is random. Okay? So this is an informal construction, but we can, of course, give a more precise construction mathematically. So I think this was given by Gregory yesterday. We identify 2 points S and T of the interval 0, 1 is the value of the excursion at S is the same as the value of T. And if it is the same, you have this property here, as the minimal value between S and T. Okay? So this property is just saying that S and T correspond to endpoints of a horizontal chord below the graph. Okay? And then you take the quotient space of the interval 0, 1 for this equivalence relation. You induce it, you equip it with the metric induced by this dE of st. Okay? Note that dE of st is 0 if and only if S is equivalent to T. That's very easy to see. So you get, in fact, a compact metric space, and the space that you get is a compact R3. Okay, this quotient space equipped with distance dE. So saying that it is a compact R3 means that whenever you take 2 points here, say A and B, for instance, you have a unique path going from A to B up to reparametrization. And this path is isometric to a line segment. Okay? So you should really think of a compact R3 as a connected union of line segments, as on the picture, which is a tree in the obvious sense that there is no cycle. Okay? Of course, here the tree is a little bit complicated. You have to take infinitely many segments and to take the closure, but basically this is the object. Okay? So things that you have of course a canonical projection from the interval 0, 1 onto the quotient space. You can root the tree at this point O, which is PE, the canonical projection, evaluated at 0 or at 1 at the same point. You have a volume measure, the push forward or Lebesgue measure. And something which is important later is the fact that you have also a way of exploring the tree, if you want running around the tree, exploring the tree clockwise, simply by using this canonical projection. So if you look at what this canonical projection here does here, it explores the tree from the left to the right. You have a planar structure until it comes back here to the starting point. So that's why I say it's cyclic. So you can move around the tree, that's the idea. Okay. So here a simulation due to Igor Korczewski. And okay, there is another ingredient I need to construct my models of random geometry, which is Brownian motion indexed by the Brownian CRT. Okay, that's going to be important. And so in a sense, what we are going to do, we are going to assign labels to the point of the tree. Okay, and these labels will evolve like Brownian motion. Okay, so this is why I call it Brownian motion indexed by the CRT. Okay, more precisely, conditionally on the CRT here, you introduce this random process indexed by the CRT, which is just a centered Gaussian process, which is 0 at the root, and such that the variance of the increment between 2 points A and B of the tree is just the distance between A and B. So it's just like the usual definition of Brownian motion indexed by the half-line. Okay? There is a technical difficulty, but which is very easily solved. So I don't explain that. So you should use this ZA as a Brownian label assigned to the point A of the tree. Okay. And as I said before, when you move along a line segment of the tree, your label move like linear Brownian motion. Okay? So there are many motivations for studying these objects independently of the models of random geometry, but of course I'm not going to describe this here. Okay, so here are very schematic pictures, but I think they help understanding what's going on. So essentially, on what I've looked at, what I consider here on the left here, on the right is a tree. Okay, you should think of it as an object like this, the root here. And on the left part of the figure, these are the labels. Okay, so the labels form a collection, if you want, of Brownian paths, of branching Brownian motions, you should say, whose genealogy is prescribed by the tree. Okay, so my picture is very misleading because all these blue paths here, they should intersect a lot. And of course, I do not make them intersecting for the clarity of the picture, but should imagine that they intersect. Okay, and well, you should also realize that the horizontal coordinate here is the label. Okay, the vertical coordinate corresponds to the distance from the root. Okay, so each point here in my picture corresponds to a certain vertex, a certain point in the tree, its label, and its distance from the root. Okay. And how do you get this tree of Brownian paths? Well, it's very easy to understand. Suppose I want to construct the label of a point A1 in the tree here, vertex A1 here. What I do, I look at the line segment between A1 and the root, and the evolution of labels along this line segment is given by a Brownian path. So this is, if you want, the black path here on my picture. This is supposed to be a Brownian motion. Beware that time for this Brownian motion is a vertical coordinate and space is the horizontal one. And you look at the value of this Brownian motion, okay, exactly at the time which is a distance from the root to the point A1. Okay, and this gives you the label, the A1. Okay, so that's very simple. And of course, if you take another point A2, so A2 is here now, you can similarly look at the evolution of labels along the ancestral line of A2, the line segment between the root and A2. And this evolves like a linear Brownian motion again. This time it's a green path. Of course, the evolution of labels is the same as for A1 up to this level, which corresponds to the branching point, if you want, of the ancestral lines of A1 and A2. Okay, so you see it's a very simple object. And now I can define the Brownian sphere with these objects. So I have these two ingredients, the Brownian CRT, and the other one, which is Brownian motion, the Brownian labels assigned on the CRT, or if you prefer, Brownian motion indexed by the CRT. Okay, so there is something a bit mysterious, which is to introduce this function d0 here. D0 of AB, when AB are 2 points of the tree, is just the sum of the labels of A and B minus twice the minimal label between A and B. What does it mean between A and B? So you have to look at what I call the interval from A to B. Remember, you have this cyclic exploration, so this means that you go from A to B, exploring the tree in clockwise order. Okay. And of course, the other one, exploring the tree from B to A, is different, of course, because of course it would correspond to counterclockwise order. Okay. Okay, so you have this function d0 of AB, which is symmetric, but which does not satisfy the triangle inequality. So you introduce another function, d of AB, which is the infimum of these quantities. This is, if you want, the maximal symmetric function of A and B, which is bounded above by d0 and satisfies now the triangle inequality. Okay? And you define an equivalent relation, A equivalent to B, if and only d of AB is equal to 0. It turns out to be equivalent to d0 of AB equals 0. And you take again the quotient space of the tree for this equivalence relation. You equip it with the distance induced by D, and this is the Brownian sphere. Okay? So maybe I can summarize the construction. What you do, you start from this tree, the Brownian CRT, so again the same simulation as before, and you glue together certain pairs of points, and two points, A and B, are identified if they have the same label, and if you can go from A to B around the tree, clockwise or counterclockwise, encountering only points with greater label. Okay, so imagine that your point A is here, the point B is here. It means that you go around the tree from A to B, and you have to, it's a very strong condition, you have to meet only points which have a greater label. Okay? And in fact, you do not identify many points, but still you drastically change the topology. You start from a tree, and the Brownian sphere is topologically a sphere, so it's very different from a tree. Okay, so a word about distances in the Brownian sphere. So it's maybe useful to introduce this particular point rho star, which is not the root of the tree, which is a point with minimal label. And then the distance d from rho star to any point A is just the label of A. You have to subtract the label of rho star. Okay? So essentially, distances here correspond to labels. Of course, if you remember the Corey-Vauquelin-Schaeffer bijection or the Boutier-Di Francesco bijection, you have a similar property, of course. Okay, so here I wrote this for points in the tree, but this means that now if you look at the Gaussian space and you take a point x in the Brownian sphere, it also inherits a label from the corresponding point in the tree. Okay, it's an equivalence class of points in the tree. And so you get that in the Brownian sphere, the distance between any point x and this particular point x star corresponding to rho star is just the label of x minus the minimal label. Okay, so of course you can do that, but you have no such simple expression for the distance between two arbitrary points A and B, but you have an upper bound. Okay. This is also very easy to understand if you come back to the bijections between, say, quadrangulations or more general planar maps and labeled trees. Okay. Okay, maybe a couple of open problems. Of course, it would have been very nice to be able to characterize the distribution of, characterize the so-called k-point function. So the distribution of the mutual distances between k points chosen independently according to the volume measure. So this is relatively easy in one case, in the case k equals 2. And because then in that case, the 2 points which are chosen according to the volume measure, you may take them, you have to justify it of course. You may take the first point to be this rho star before, and the second point to be the root of the tree. And then you find that the distance is just minus the minimal label on the tree. Okay? And for this you have, okay, you can get information. So I wrote down, there are also other expressions, but I wrote down a result of Delmas which characterizes in fact the distribution of this d of rho star rho, so the 2-point function. But then if you come to k equals 3, it's much harder, and so there is this nice paper of Jérémy and Emmanuel, which obtains the asymptotics for the 3-point function of large quadrangulations, and so this gives, in fact, in the limit, the 3-point function of the Brownian sphere. Okay. But this becomes quite complicated, and it seems, higher values of k seem intractable. Well, one never knows, but I also mentioned an interesting one problem which concerns Voronoi cells. And there you take k points distributed according to the volume measure, the Brownian sphere. And you consider the associated Voronoi cells. So Ci is just the set of points which are closer to Xi than to any other Xj. And then there is this conjecture by Guillaume Chapuis that the distribution of the k-tuple formed by the volumes of the Voronoi cells is uniform over the simplex. Okay? And this is a very intriguing problem. And we have only one particular case, which is due to Emmanuel, in the case k equals 2. Okay? And other cases are still open. I'm not completely convinced that the conjecture is true, by the way, but it turns out that I did not give the references, but it turns out that the analogous result for the tree is known to hold. Okay? If you look at the Voronoi cells now in the tree for the metric of the tree. Okay. Okay, let me turn to local times. Sam. So just a reminder of the notation. This Z is Brownian motion index by the CRT. We can look at the occupation field of this Z. Okay, it's just the push forward of the volume measure under the mapping A gives ZA. And well, just a comment, this occupation field is just what people also call the ISE, integrated super-Brownian excursion. Okay? And we have the following fact. So I put several references here because essentially this result was in some form already in the work of Sugitani, which was concerned with superprocesses. So it was a slightly different context, but it's really almost the same object. Then there's this paper by Mireille and Svante Jansson, and a more recent paper by Guillaume Chapuis and Jean-François Marquer, saying that in the end what we get is that this occupation field has a continuously differentiable density. Okay, so I will denote by here dot LR the derivative. So we call LR the local time at R, and in some sense it measures the size of the set of points in the tree which have label A. Okay. So
may I ask a question, Jean-François? But the measure is O is random, right?
Yeah, of course. Yeah.
So here you mean that it's almost surely it has almost surely a continuously differential density?
Well, you mean there should be? Yeah, there should be an almost surely.
Almost surely.
Yeah. Okay. Right.
So it's a random. The derivative is a random function.
It's a random measure which has almost surely a continuously differentiable density. Yeah. Okay, so what I'm saying is that, again, on my very basic picture here, that if you fix R, you look at these red points correspond, if you want, to points in the tree which have label R, and your local time measures how many red points you have. Typically, you have infinitely many such points, of course, but there's a way of defining the quantity of these points. Okay. Okay, so in terms of the Brownian sphere, if you remember that the distance in the Brownian sphere is given by the label. Well, you have to subtract the minimal label here. Distance from this X star. You'll see that the local time at level R will correspond essentially to the volume of the sphere of radius R minus Z star here in the Brownian sphere. Okay? It's just this equality is trivial. It's just the definition, if you want, of local times. And here you see that what you get is the volume of the spherical shell, if you want, in the Brownian sphere, limited by the radius R minus Z star and R minus Z star plus epsilon. Okay? When you let epsilon go to 0, you can interpret this as the volume of the sphere. Okay. Yeah, there are other ways of justifying it, but okay. So one question is now: how can you describe, in fact, the distribution of the process of local times when R varies? Okay. And here there is a recent paper by Chapuis and Marquer, which was based, in fact, on very nice discrete results for, I think, for enumeration of embedded trees due to Mireille Bousquet-Melou and Guillaume Chapuis. And they conjectured that the process of local time satisfies a certain stochastic differential equation, which I have written here. And here B is, as usual, a linear Brownian motion. Okay, so you have, this is a diffusion part. So you should notice that this is for the derivative of local time, but here you have the local time. So it's really a kind of two-dimensional problem, certainly. And also, here in the function G, they expect to have this integral of the local time, okay? With a certain, they do not identify the function G, but okay? And this is still an open problem, in fact, but as we will see next, if you slightly modify the model, you can prove, in fact, this conjecture, okay? So by slightly modifying the model, I mean that I'm going to work with what may be called the free Brownian tree or the free Brownian sphere also. And what is it? It's exactly the same construction I gave for you for the Brownian CRT, but I do not deal with a normalized Brownian excursion, but I take a free Brownian excursion, okay? And a free Brownian excursion means that it is distributed according to something which is very classical in the study of Brownian motion, the Ito measure, okay? And if you are not familiar with that, you should just imagine that the duration of the excursion now is random. You have it's not prescribed to be equal to 1. Okay? The duration of the excursion corresponds to the volume of the tree. So you also have a tree with a random volume. Okay? And this object, in fact, is in a sense nicer. Well, well, it has nicer properties than when you condition the duration to be equal to 1. Okay. Okay, you can again consider the occupation field. Again, you have a continuously differentiable density. There is nothing new there because you just have to do a scaling by a random constant if you want with respect to the case of Brownian motion index by the CRT, and you, of course, the scaling does not change the fact that you have a density. Okay, so we'll see that the conjecture holds in that setting. But before doing that, let me explain first that we have a Markov property of local time. Okay, so this is to remind you of the notation LR and the derivative of LR. If you look only at LR, clearly it's not a Markov process. Okay, because if you say, suppose you fix H positive and you want to predict the future, so the values of the local time for R greater than H from the past, so values for R less than H. Saying that it's a Markov process would say that to make this prediction, it's enough to know the value at H, for R equals H. Okay? But here it's not sufficient because you also need to know at least the derivative. If you know the past, you know the derivative. Okay? And it turns out that this is sufficient to know the derivative, that the pair consisting of the local time and its derivative is Markov. Okay? And here I look only at positive values of R, but in fact, it's sufficient because if you have a symmetry property. Okay. Okay, so maybe I omit. Okay, maybe I do not discuss that. So just saying that to get this Markov property, you need a kind of excursion theory, but it would be a bit too complicated to explain it. Okay, so then you can prove that you have a stochastic differential equation for these local times. So these are the local times. I remember you as this capital L here correspond to the local times for the free model, for the model of Brownian motion indexed by the free Brownian tree. Okay. And then you have, so I wrote 2 lines here, but the first line is just saying that L dot R is a derivative of LR. Okay. So the important line, of course, is the second one, where you have an equation of the type that was conjectured by Chapuis and Marker, but here, in a sense, it's even simpler because your function G depends only on the local time and its derivative. Okay, and okay, so this is the diffusion part. In fact, the same as was conjectured by Chapuis and Marker. Okay, and what is this function G? You can identify it, in fact, in terms of this function PT, which is a stable density with index 3/2. So it's okay. I have a more precise definition here. You can characterize it, in fact, by a kind of Laplace transform, which is given here. It's stable with labeled with index 3/2 because you have this lambda to the power 3/2 here. Okay, and I have also this p prime t, which is just the derivative, of course. Okay, so this, if you want, this is the Chapuis-Marker conjecture for the free model. If you want to get the same conjecture in the original form for the ISC, you need to condition on the total mass equal to 1. Okay, the total mass is just the integral of the local time. So you need to condition on this event. So you have to take the solution of this problem and to condition on this, and to see that even after this conditioning, well, you again have a stochastic differential equation, but with a more complicated form. Okay. And this is not completely obvious, even this probably can be done. So it turns out that this drift that we get here, the drift is the function G in the equation here, can be expressed in terms of the classical Airy function. And in fact, essentially it is obtained from this function script capital A, which is defined in terms of the classical Airy function AI here. This function script capital A is in fact called sometimes the map Airy function. So it appears in particular in the book by Flageolet and Sedgwick, and it's also related to some properties of random planar maps. Okay, and okay, so you have an explicit expression for G in terms of this function script capital K. Script capital A is basically the derivative A prime over A here, evaluated at this t minus 2/3 times y. Okay. And okay, so now I will come to the last part of the lecture. I have 10 minutes, I think. I will speak about volumes of spheres in the Brownian plane. I think it's perhaps the nicest application of what I've described before. So what is the Brownian plane first? The Brownian plane is just an infinite volume version of the Brownian sphere, so it can be constructed in very much the same way as I constructed the Brownian sphere at the beginning of the lecture, but I'm not going here to give this construction. It would be too long. You can view it as a tangent cone in distribution of the Brownian sphere, meaning that you start from the Brownian sphere, you multiply the metric by a constant lambda, you let lambda tend to infinity, and in the limit you get the Brownian plane. Okay, well, in a suitable Gromov-Hausdorff sense. Okay. It is also the scaling limit of the uniform infinite planar quadrangulation or triangulation. Okay. And it also arises, in fact, as scaling limit of random planar maps with a finite number of faces, provided you rescale by a factor which is large in comparison to n to the power minus a quarter. So this n to the power minus a quarter is the usual rescaling for planar maps with n faces, but here you rescale by a larger factor, and of course in the end you get an unbounded space, but which is the Brownian plane. And the Brownian plane turns out to be very closely related to the Brownian sphere. Of course, it has the same local properties as the Brownian sphere, meaning that you can couple Brownian sphere and Brownian plane in such a way that the small balls centered at the distinguished point are the same, are isometric. Okay. So I forgot to say, it's very important, the Brownian plane also comes with the distinguished point here, which I denote by x0. Okay. And of course, we saw in the Brownian sphere, we also had this point x star, which was distinguished before. So just an artistic view of the UIPQ. You should think of it as an infinite random lattice in the plane made of quadrangles. Okay, so the result is that if you look at this object, but you equip it with a graph distance, but you multiply the graph distance by a factor tending to 0, and in the limit you get the Brownian plane. Okay. Okay, here are some properties of the Brownian plane. Maybe I'm not going to say too much about that, except that the first property is going to be important. You have a scale invariance. If you multiply the metric by any constant, positive constant, of course, you do not change the distribution of the space. Okay. What is also nice in the Brownian plane is that you can make more explicit calculations, in fact, than in the Brownian sphere. Okay. So I've given an example there. Okay, so let me turn now to volumes of spheres, and for that I introduce a profile of distances. So this is again just the push forward of the volume measure in the Brownian plane under the mapping x gives the distance from the distinguished point. Okay, and again you have continuously differentiable density for this profile of distance. And so you can define this density, you can define the local times as this density, okay? And things are slightly nicer here than before. So the local times can be viewed as a limit of 1 over epsilon times the volume of the spherical shell between the radius r and radius r plus epsilon. So it's very natural to interpret lambda r as the volume of the sphere of radius r, okay? Okay. So, in fact, why do we have this fact here, this property? Simply because it's really a very easy consequence of what I said before. Since we have this coupling with the Brownian sphere, you can see that the profile of distance in the Brownian plane coincides near 0, okay, near 0, with a similar profile of distance from the distinguished point in the Brownian sphere. And in the Brownian sphere, we know that this profile of distance, the fact that distances are given by labels, that this profile of distance is just the occupation field of Brownian motion indexed by the Brownian tree, up to a shift. Okay? You remember we had the shift by the minimal label. Okay? So this one is known to have a continuously differentiable density. So it will also be true for this profile of distance. It will have a continuously differential density near 0, because this works only near 0. But then you can use scale invariance. If it works near 0, it has to work everywhere. Okay. Okay. So what happens for the process of volumes of spheres in the Brownian plane? Well, you can again prove that the local time and its derivative satisfy is a Markov process and satisfies this stochastic differential equation. So it's not exactly the same as before. There is a function h, which is given here now by this formula. And of course, B is again a linear Brownian motion. Okay? And of course, this is closely related to the one we had before, the stochastic differential equation for local times of Brownian motion indexed by the Brownian tree. But the drift is different, okay? Before I had this function g, which was the drift. Now you have this function h, which is related to g, but not exactly the same, okay? So how do we get the result? Again, there is a coupling argument, the one I mentioned before. You can, turns out that you can couple the Brownian plane and this process capital L are corresponding to local times of Brownian motion indexed by the Brownian tree in such a way that for small values of r, okay, you have the fact that the local time lambda r, well, it should be the L evaluated at the substar here plus r, but in fact by symmetry you can as well put here, it will be more convenient, L taken at the maximal label minus r, okay? So you can couple the two local time processes, and you know, this is the first theorem I stated, that this L satisfies stochastic differential equation. It's written here. And moreover, this Z star here, turns out this is a maximal label, or it's also the first R, is the heating time of 0 by the process of local times. Okay, this is known. Okay, and so this suggests time reversing. It means that we have to consider this diffusion process, but you to time reverse it because you have this star minus R here at the stopping time Z star. And first, when I started to work on that, I thought that it would be very easy. And finally, it took me a long time to do this because you cannot really apply the classical time reversal theorems in this setting, or at least I wasn't able to do it. So there is another idea which is important, which is to introduce an auxiliary process. So this is a bit of standard stochastic calculus, but you have to write it down. It turns out that the equation that is satisfied by the local times L, this LR here. Okay, so it's a two-dimensional equation, in fact, because you need to have the local time and its derivative. But you can, if you do perform a suitable time change, you can write everything in terms of a one-dimensional diffusion process. Okay, so I've introduced here the corresponding time change to S, the infimum of the inverse, if you want, of these integrals here. And it turns out that if you look at the local time evaluated at tau of S, you can write it as local time at 0 times this exponential involving this process capital X, which is a solution now of this one-dimensional stochastic differential equation, with the function B, which you can again identify explicitly. And this process, so this is something which is very well known, that such a solution of SDE under appropriate condition on B, which are satisfied here, gives you a nice ergodic one-dimensional diffusion process, and which is time reversible under its unique invariant measure. Okay, so one may use this time reversibility to study the process here, but still there is some work to be done. It's not, again, so straightforward. So maybe I skip that. And just to give you perhaps a more geometric interpretation. So here is a kind of cactus representation of the Brownian plane. You see, so the distinguished point here, x0, is at the bottom. And vertically, this is the distance from x0. So you have, okay, you have something which is homeomorphic to the sphere, but which looks roughly like this cactus, okay? And if you fix a level R, you can look at the connected components of the complement of the closed ball centered at x0 with the radius R. here I've drawn only 3 of these components, but there are infinitely many of them. C0 there's just one unbounded one. I called it C0 here. Okay. So what the local time does is measuring the sizes of the sphere, okay, of the set of points at distance r. So this is a set of points in my picture which are at this level here, if you want the red point. But the picture is very misleading because most of these points do not lie on the boundary of any connected component here, the complement. Okay. And in fact, the derivative here corresponds to some sense the sum of the boundary sizes of the components, okay, except that the sum diverges. So you have to renormalize it, but it can be done. It's not a problem. So it explains a little bit how these local times evolve. Okay, so there are open problems. Okay, it's already late. So an open problem would be to prove I forgot, this is the Chapuis-Marker conjecture, yeah, for the density. So as I said before, you would need to condition everything on this event here, okay? Total volume equal to 1. It's interesting to compare this with what one knows about local times of Brownian excursion, classical local times, okay? The case of the free excursion, it's a very famous theorem due to Reinhardt, in fact. But if you look at the normalized excursion, it's much harder. But this has been done by Jim Pinbat, okay? Or another question is to prove strong uniqueness, in fact, or even weak uniqueness for this equation starting from 0, 0. And we realized that even for simpler equations like this one, you can have problems with the uniqueness of the solution, okay? So it's not so clear. Okay, thank you for your attention.
Thank you, Jean-François. So, other questions?
Yeah. Sure.
So with the original problem in the CRT, you have this discrete counterpart of your problem with discrete trees of fixed size carrying labels on their vertices. And so would there be also a discrete counterpart of the free problem with some question asked on some families of trees, maybe of non-fixed size or infinite size? Or?
Yeah, sure. You just have to consider Galton-Watson trees, in fact, or simply generate it. It's the same. Well, Galton-Watson trees, okay, where you have you start with say one root where you have a random number of children, which have a random number of children, and so on. Usual branching process tree. And then you can also look at local times. It's not completely clear for me how to define the local times, but my student, I don't know if he's here today, Alexis Metz-Donadieu has been studying that. What you can do, for instance, you can look at, for each integer r, you look at the number of edges r plus 1, and also the number of edges r plus 1 r. Edges are oriented from the root, okay? And if you look at this pair, what you get, okay, I do not give precise details of the model, but you again get a Markov property. And you may, I think you can also perhaps understand the Markov property in the discrete setting from the discrete model. But what would seem difficult would be to recover the stochastic differential equation, okay? But maybe it's possible, probably. I'm not sufficiently expert in discrete calculations, so but it's essentially you have to look at generating function. For instance, if you start, what would I say? Just maybe start just with one edge, 0, 1, and you let the process evolve, and you want to know the generating function of the number of edges which. Yeah, I think perhaps you want to know how many edges return to 0 and for this model. And there are things you can calculate. I think I sent you an email about what could be computed.
Yeah, recently. So it was about that. Okay.
This was related to that. Yeah, you just have to look at my email.
Okay, so I will reread your email. Thank you.
No, but I was
This is
giving you
embarrassing.
only the recursive equation for the generating function.
Yeah,
I was not
remember
giving you
this.
the interpretation.
Yeah, there was some suspense. Okay, thank you.
But what becomes the size? The fact that your times t equals 1 becomes 3.
It's because the number of vertices, if you have a Galton-Watson tree, it's random, of course. So if you, okay, how can I say that? Your Galton-Watson tree, it has a random number of vertices, okay? So this corresponds to the fact that in this free model, my Brownian excursion also has a random length, if you want, okay? So if you, or something you can do, you can, suppose your Galton-Watson tree, you condition it to be large, say to have a height greater than epsilon, or greater than n, or something like that. And if you rescale it properly, you will converge to this free Brownian tree with a certain conditioning also. Yeah, but you do not fix the size of the tree.
Any other questions? Michel?
Wow.
Yes, there is an exponent 1/3 in your time change.
Oh yeah.
And is there any interpretation of this 1/3 or minus 1/3?
Yes, that's a good question. So, no, it's not an interpretation, but I can just say that near the extinction time, near the moment when the local time becomes 0, when you reach the maximal label, this behaves like you look at the label. So, how do I call it? Z star was the maximal label, so you look at the label at Z star minus epsilon, say, and then it behaves like epsilon to the power 3. Okay, the same. Okay. But it's just a comment about you have get this factor 3 again, and also you have relations with okay, but this 3-half is the same as in other problems, but no, okay. I should think more about your question. Yeah, it's not so clear.
Thank you. Any other questions? Okay. I think rather than a question, I have an anecdote to tell, because here it's the point of that. It involves indirectly you, Jean-François, and also Emmanuel. So a few weeks ago, in our project with Emmanuel and Hugo, Emmanuel did a computation using the things we do, involving analytic combinatorics, saddle point method, and he computes something, and if we believe our context, he said it should be, okay, maybe we will not use the term that you use, which is the two-point function of a stable tree of index 3/2. And probably it's the quantity that appeared in your slide, if I understand correctly. Okay, so Emmanuel, you did the calculation and said, oh, but is it really the two-point function of a stable tree of index 3/2? And I was in Jussieu at the time, in the evening, and I said, okay, I should ask the question to a real probabilist. And I say, what's the point of being in Jussieu if I'm not able to? I could have asked Gregory or you, etc. But if I moved to Jussieu and I was expecting to have a probabilist next to my door. So we have a WhatsApp group, so I send a message and saying I have an urgent question about stable trees. But, okay, the person I had in mind was Thomas Duquesne, but you know Thomas is a bit busy in administration already, etc. So it took a while, and I wanted to see if I had power to summon a probabilist to my door. In the end, it took half an hour, but Armand Riera came, and he explained me a few things, and what he did is that he pointed me to a specific result in the notes you wrote with Thomas, etc. And he did help me to do the translation, and after he put me to that, and I sent it to Emmanuel, and after that we checked that it was indeed right through. So the moral of it is that we should thank you, but also we need someone to help us to do the connection and to translate results from one another.
You can ask Armand.
Armand is quite good.
He's
very good for that. Okay. So thank you, Jean-François.
Well, thank you.
Okay, so this.
I think we should all thank the organizers of this wonderful meeting, which I enjoyed a lot.
Thank you very much. And since this meeting is coming to a conclusion, we have to say a few words. Words to thank first all the invited speakers who did a wonderful job of giving. Speaking of lots of interesting research, which has the interaction with what Emmanuel did. Thank you to all of you for coming. We also have to thank, I think, important to thank the people who allow us to be there. So there are, of course, the institutions, the money received for this from mostly from Institut Physique Théorique and the CAA and CNRS institution, and then the ERC of Bertrand Hénard. Renew Quantum help us fund everything. And more important than institution, there are people. So the people who help us set up this are Laure Saubois and Camille Floret, whom you have met. And okay, many other people, but more specifically them. And also Fabien from the technician there. So I think we should applaud them for their help. And of course, thank you for all for coming, and I think Bertrand, you want to say a word first?
Just very, very short note. Yesterday, I just forgot to do one thing, which I could not do actually at the dinner, just to give a present to Emmanuel before he gives a few words. But now, in public, he can't refuse it. So here it is for you, Emmanuel. You will understand the meaning of this later once you open it, but not now. So now I give you the microphone.
No, what?
He doesn't like to travel, doesn't like to present either. So.
Okay. No, what Bertrand didn't say that he actually showed me the present and say, "Can you take it? But don't open it." And just he wanted me to take it in my car, so so he doesn't have to carry it. That's all. That's why I didn't take it yesterday. Okay. Anyway, I will. You want me to open it? You want me to? I don't open it. Okay. No. I keep it, but I don't open it. Okay. So I also want to say a few words to close this conference. I'd like to say thank you to first thank the organizers, Jérémy, Philippe, and the two Bertrands. I think they made a wonderful team. I think I recognize one as a grandmaster, another one as a master of requests, third one as the grand treasurer, and of course the grand chamberlain or grand camerlingo, as you want to call it, from whom I tried to extract as much information as I could, but still I didn't see yesterday's surprise coming, so that was a really nice surprise. Thank you. Okay, so of course I thank you as colleagues, very valuable collaborators, but also as true friends, because I mean we are really true friends. Okay, I want also to thank, as you said, Laure and Camille for their remarkable work managing all the logistics, and to thank Fabien for his great work on techniques and solving all kinds of problems. Okay, then I want to thank all my collaborators over this almost 40 years, and I think it's really crucial to have people to work with and to whom you trust 100%, so you can tell them your ideas, even if they are stupid. But so also among them, I want to thank especially François, who welcomed me in this laboratory and trusted me at the beginning of my career. I should also thank André Morel, who was the head of the department when I was hired. So he offered me this job in this great laboratory. So I owe him a lot. And there are also 3 collaborators which I would like to mention because they stand out for some very special reason, which is I never met them actually. So one collaborator is in the paper with Charlotte, which was mentioned because several times because it was the first time where we recognized that some meander-like problem could be solved in some sense by the K-Bezier relations. And the second problem was also Mark talked about it yesterday. It's a nice paper we did with Jeremy and Mark Bowick and another collaborator, which I never met. Okay, and he did the numerics, and that was very, very, very nice results, very nice numerics. And for instance, we were able from the numerics to, it's a sliding problem where you have dimers which slide and on a square grid, and it's full of dimers except there is a hole somewhere and you can slide, but in some cases you cannot slide anything, so it's completely jammed. And we computed the probability, and Mark mentioned that already, and the result is, we had an estimate of the result, but with 20 digits, so we could figure out that the result was 57/4 minus 10 square root of 2. So that's the probability of being completely jammed, so you cannot make any move. And then we also we evaluated numerically the probability that you can make one move, only one move. And we had 16 digits, but we were not able to figure out what it was. And then it was proven a few months later, and I have to take my notes because the result was probably being able to make one move is 1/32 and 7 square root of 2 minus 977. Okay. So that's why we couldn't figure out what it was. But actually, the 16 digits were correct. Okay, so great numerical work. And the third collaborator, which I never met with you on the 20 vertex model. So the numerics, most of the numerics was done by Brian Debin, who actually made a remarkable work too. Okay, then I'd like to thank all the speakers, of course, for their very nice presentation. I'm always fascinated by, to see how new ideas emerge, and I found all these talks very inspiring. And also, of course, I want to thank you all for being here, because this conference was a bit special with some physics talks, real physics talks, and some mathematical talks with real mathematics. And I hope the physicists were not too lost with mathematics and conversely, but I'm sure, everything was understandable, more or less. And so I myself find it very comfortable to be in between these two domains. I should say what I like about physics is the possibility to make explicit calculations. It's sometimes heavy and extensive calculations. And I learned in my thesis how to make flawless calculations for dozens of pages. And also what I learned from physics is you shouldn't be afraid of any calculation. If you can't do it, probably you can do it. Okay, and then about the mathematical side, what I like, especially, of course, because it's combinatorics, is the possibility to make experiments, actually. Because you compute numbers, but then you can check really that they are the good numbers by just first looking at the first numbers, and then you can also predict exponents and check that they are correct. And I think that computing an exponent is nice, but measuring it like a real experiment is even nicer. So I thank you all for being here, and see you soon. Thank you.